Hey class, this is Gigi. In this optimization problem, we are making a box out of a square piece of cardboard. Okay, so you have a square of length S, and you're gonna cut X out of each of the corner. You're gonna cut X out of each of the corner. So then your dimension would be S minus 2x by s minus 2x. So when we do look at the box that we have here, we are going to say that this box is going to have the dimension of 2, this is the s minus 2x multiplied by s minus 2x multiplied by the height, which is x. Okay, so when we do look at the volume, we would say the volume of this box is going to be x multiplied by s minus 2x squared. Okay, which if you multiply this out, it would be x multiplied by s squared minus 4sx plus 4x squared, and then you distribute in the x, the volume would be, let's write them in, let's go ahead and just distribute. S squared x minus 4s x squared plus 4x to the third. All right, so now what we're going to do is we are going to take the derivative, right? So you can take the derivative of the volume, because what we want to do is find out what the maximum is. We're optimizing this this problem. All right, so this function. So then the derivative would be, I'm writing that in order, 12x squared minus 8sx plus s squared, where s is the dimension of that original square. Okay, so that's a number. That's a fixed number. It's not a variable. So we don't need implicit differentiation here. We're treating s as a constant. Okay, so then we would say, well, the derivative is going to equal to 0 when we can actually factor this out and solve, right? And plus s squared, so at the end you'll have plus s, and then I would have to choose a combination that multiply to give me 12 and add together to give me 8, and I can see that that would be 2s and 6s, but I need to make that minus 8s, so I am going to have that being minus. Okay, so that would be minus minus, not plus plus. So we will say that is going to be minus minus. And so when we solve, we would say, oh no, that's not s in the front, that should be x. Because we are still trying to solve for x. Okay, so then x would be s over 2 or s over 6. Now let's justify which one of those is your answer. Well, we cannot let x be s over 2, because if you cut half, right, and then you cut the other half like that, you won't have a box. So that's not your answer. Okay, so that's not your answer. So x will have to be s over 6. Now, what you'll do is you'll need to confirm that that really is your maximum. So in this problem, instead of using the first derivative test, I'm going to go ahead and use the second derivative test. So the second derivative of x is going to be 24x minus 8s. When I evaluate it at s over 6, right? If I put s over 6 into there, I will have, into here, I will have then 4s minus 8s, which is negative. That will be negative 4s. And it's negative. If it's negative, then my function is concaving down at that point. So that is going to give me a local maximum. In this case, really, it's the maximum of our interval. Okay, so our interval gonna go from the smallest would be, the interval would be 0 to s over 2. And as you can see, s over 2 is going to be your biggest, right? So s over 6 is in between there, and it's going to be a maximum. So then the maximum volume will be x, which should be s over 6 multiplied by s minus 2 times s over 6 squared, and that would be s over 3. And so that really is going to be s over 6, and then I have 2/3 squared. That would be 4 over 9 s squared. 4 divided by 2 is 2. 6 divided by 2 is 3. So really the maximum volume is going to be 2 over 27 s to the 3rd power. That is our maximum volume of the box that is made out of a square cardboard. So now, if you know the dimension of that square cardboard that you had originally, you can just plug it into there, and that should give you the maximum value for the volume that you want.